Hydrostatic forces on curved surface. Curve. The resultant pressure on a curved surface is most easily computed by separating it into horizontal and vertical components. For example, consider this picture for more description. From this picture, we can show that the resultant forces on a curved surface in which is submerged in a fluid in a static position, and the body diagram is shown in this figure. So we can write equilibrium condition. We have these relations FH equals to in this case FH, which is horizontal force on a curved surface, equals to the horizontal component of the force here, right? The horizontal component of force on a curved surface equals the force on the plane area formed by the projection of the curved surface onto a vertical plane normal to the component. This projection of the curved surface normal to the component, which is our component, so we can consider a flat plate submerged in a fluid which have, for example, a central gravity, central point of central gravity. We have also central point of pressure, and the force equals to the relations that discussed in the previous section, and the normal vertical components are, let me write, the vertical component of pressure, force on a curved surface, equals in magnitude and direction the weight of the entire column of the fluid. The entire column of fluid. Both liquid and atmosphere above the surface. It shows in this picture, if you look at this picture again, the weight of the, for example, those atmosphere, the first fluid block, which is a rectangular, and also the second floor block, which is a curved area, and there is relation for CG and for example this area and CG, the point of application of weight force. With a momentum, making a momentum on any point, we can calculate the point of reaction. Anyway, we are going to continue our discussion about hydrostatics force in layered fluid. The formulas for plane and curved surface in the previous sections are valid only for a fluid or uniform density. If the fluid is layered with different densities, such as this picture, so if the fluid is layered with different densities, such as these two fluids shown in this picture here, and here we have two different fluids with different densities. A single formula cannot solve the problem because the slope of the linear pressure is different, such as shown in this picture. However, the formula applies separately to each layer, and thus the appropriate remedy is to compute and solve the separate layer forces and moment. Consider the slanted plane surface immersed in a two-layer fluid as this picture. The slope of the pressure distribution becomes steeper as we move down into the denser second layer. The total force on the plate does not equal the pressure at the center times the plate area, but the plate portion in each layer thus satisfies the formula, so that we can sum forces for find the total force, we can write F equals to sigma Fi equals to sigma P central gravity multiplied to A for each fluid, and we have also I equals to rho I G sinus theta I x xi. For each component we can calculate each fluid PCGI, AI, and X center of the pressure equals to rho I G sinus theta I X. Multiply to AI. We have various formula for calculating inertia for different shapes in the reference, and you can use the appropriate formula for calculation. This formula locates the center of pressure of that particular F with respect to the centroid of that particular portion of plate in the layer as shown here. We have a X and Y for this part and this part. The center of pressure of the total force, as we said, equals to summation of each force, can then be found by summing moment about some convenient points such as the surface. There are examples in the video solution part. You can study those examples for more practice and understanding. The next discussion in this chapter is about buoyancy and stability of fluid, static fluids, static situation. Buoyancy and stability. The same principle used to compute hydrostatic forces on to compute hydrostatic forces on surfaces can be applied to the net pressure force on a completely submerged or floating body. The results are the two laws of buoyancy discovered by Archimedes in the 3rd century BC. The one law is a body immersed in fluid experiences a vertical buoyant force equal to the weight of the fluid it displaces. In a fluid, experiences a vertical buoyant to the weight equals buoyant force equal to the weight of the fluid it displaces. And 2 is a floating body displaces its own weight in the fluid in which it floats. A floating displaces its own weight in the fluid in which it floats. These two laws are the Archimedes' laws for calculating the buoyancy force and also floating force on a body floating in a fluid. Archimedes' two laws are easily derived by referring to the some problems. Consider this picture for more description of these laws. From this picture, part A, a body lies between an upper curved surface. For example, if we divided this surface to two parts, we have two forces, F(V1), which is on the upper surface and the curve, and V(V2) in the lower curve. At equilibrium, we can write equals to 0 at stability form, and the net force on the body is equals to F(V2) minus F(V1). Alternatively, the figure B also shows the body floated in the submerged in the flow. We can sum the vertical force and element vertical slice through a immersed body as the hydrostatic force. So we can write FB equal to integration of P2 minus P1 dAh equals to minus gamma integration Z2 minus Z1 dAh equals to gamma multiplied to body volume. There are identical results and equivalent to Archimedes' first law. For a floating body, the equation is also available for Archimedes' law number 2. Consider this picture for description. Let me first have a description on the buoyancy force on a floating submerged body. We integration on body and volume, P2 minus P1 dA body volume. In this equation, assume that the fluid has uniform specific weight. The line of the action of the buoyant force passes through the center of volume of the displaced body, that is its center of mass, computed as if it had uniform density. This point through which FB acts is called the center of buoyancy. The point of FB application. Commonly labeled with B or CB, buoyancy point and center of buoyancy. Of course, the point B may or may not correspond to the actual center of the mass of the bodies or material, which may have variable density. The equation in previous, which stated as FB equals to sigma, the equation above can be expressed as this relation gamma multiplied to gamma is a specific weight, body volume, can be generalized for the various fluid. FB layered flow, LF means equals to sigma rho G displaced volume I. Each displaced layer would have its own center of volume, and one would have to sum moments of the incremental buoyant force to define the center of buoyancy of the immersed body. Since liquids are relatively heavy, we are conscious of their buoyant force, but gases also exert buoyancy on any body immersed in them. For example, human beings have an average specific weight of about specific weight about 60 pound force on foot cube. We may record the weight of a person is approximately 180 pound force, and thus the estimated percent total volume if be estimated as 3 foot cube. However, in so doing, we are neglecting the buoyant force of the air surrounding the person. At the standard condition, the specific weight of air is determined. Hence, the buoyancy force is approximately for each human is about pound force. Buoyancy in air for human. Floating bodies are a special case. Only a portion of the body is submerged, with the remainder poking up out of the free surface. There are various examples related to the floating bodies in the example videos. The next description is about stability. Oh, yeah. سلام، وقت بخیر. خطای دینامیک فرمول داره برای محاسبش یا نه دیتاشو شما خودتون میدین؟ اگر فرمول داره فرمولش هم باید بدید، ولی که میدونم چقدر وقت میگیره. سلام، وقتتون بخیر باشه. من نمیدونم چقدر وقت میگیره چون داده ها رو ندیدم و همچنین نحوه محاسبه خطای دینامیک اینا رو ببینم. چند تا نمودار هستن. ممنون. Stability. A floating body, as in this figure, may not approve of the position in which it is floating. If so, it will overturn at the first opportunity and is said to be statically unstable, like a pencil balanced on its point. The least disturbance will cause it to seek another equilibrium position that is stable. Engineers must design to avoid floating instability. The only way to tell for sure whether a floating position is stable is to disturb the body a slight amount mathematically and see whether it develops a restoring moment that will return it to its original position. If so, it is stable; if not, unstable. Such calculations for arbitrary floating bodies have been honed to a fine art by naval architects, but we can at least outline the basic principle of the static stability calculation. This figure illustrates the consider this figure for various type of stability. This figure illustrates the computation for the usual case of symmetry floating body. The steps are as follows. The basic floating position is calculated from the equation. So the basic floating position is calculated from equation FB equals to gamma volume, and with the equals to FB equals to floating force minus weight of fluid, weight of the emerged body as shown in this picture. So we can write the equilibrium equals to FB equals to gamma displaced volume equals to floating force minus the weight of the submerged body. Second point in the stability discussion is that the body is titled small angle delta theta as shown in this picture. So we can write the body. The body is titled small angle delta theta, and a new waterline is established for the body to float at this angle. And a new waterline is established for the body to float at this point. The new position beta prime as shown in this picture is the buoyancy. The buoyancy is called curated. Buoyancy center of effect, a vertical line drawn upward from beta prime intersects the line of symmetry at the point M, called the meta center, which is a dependent of delta theta for small angles. And for the tree, if point M is above G, a restoring moment is present and the original position is stable. This picture is stable. Position is stable. And if point M is below G, position is unstable. So we are going to continue our description about stability with the stability related to waterline area discussion. Stability related to waterline area. Naval architects have developed the general stability concept from the previous figure into a simple computation involving the area moment of inertia of the waterline area about the axis of tilt. The derivation assumes that the body has a smooth shape variation near the waterline and is derived from this figure. Consider this figure for deriving the equation. The y-axis of the body is assumed to be a line of symmetry. It's shown in this picture here. Y-axis. Tilting the body a small angle theta as shown in this picture. Theta is here. Then submerge a small wedge OBD and uncover an equal wedge OCOA as shown in these two wedges. These two wedges. The new position beta prime of the center of buoyancy is calculated as the centroid of the submerged portion AOBDE. A O B D and E. So we can write the relation x bar volume of AOBDE equals to integration x dv on the volume v equals to AOBDE So we are going to show A, O, B, D, E portion of the floating So we have this relation x bar multiplied to v floating equals to two parts, this part and this part, v1 plus dv v2 equals to we can write again this shape to integration of x dv on v prime 1. We can write also with the different shapes. We can use this shape plus this shape minus this shape. We can now write v prime 1 x dv plus v prime 2 x dv minus v3 x dv. So we can write the areas and calculation. The first we have 0 plus the second is integration x l dA plus, let me show the picture here too. We can show the v1 v2 is v prime 1 and v prime 2 is this portion of body. So we should subtract this triangle to result a shape as the submerged body here, this type, this shape. The distance of the first volume is to the center line is 0, so we write here, and the second we have a d element dA. Here the dA dV equals to LdX LdA plus minus the again x LdA. We can write a expression for dA equals to x tangent theta dx. So we can write the integration as follows: x multiplied to L multiplied to x tangent theta dx plus the second integration is minus x L minus x tangent theta d theta. So the result is tangent theta to x2 L tangent theta dA, which is equals to tangent theta x2 dA. So the results are equals to I/O tangent theta. This relation says that where I/O is the area moment of inertia of the waterline footprint of the body about its tilt axis O, the first integral vanishes because of the symmetry of the original submerged portion CODEA as we said before. The remaining two wedge integrals combined into I/O when we notice that LdX equals to element of waterline area. Thus we determine the desired distance from M to B. We can write this formula for the geometrical analysis of the floating body. X bar equals to I/O mg plus gb, or mg equals to the engineer will determine the distance from G to B from the basic shape and design of the floating body, and then make the calculation of I/O and the submerged volume V sub submerged volume. If the metacentric height mg is positive, the body is stable for a small distances. Note that if gb is negative, that is b is above g, the body is always stable. So if gb is negative, we have a stable position for a tilt body, floating tilt body. There are examples in solution part. The next description in this chapter is the pressure distribution, rigid body motion.